Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss problems on pulse code modulation. In previous session we discussed the problems on quantization. Now we are going to solve problems on PCM. So we know that PCM, pulse code modulation, this is the basic digital modulation system, and the features of PCM having a region repeater in the transmission path. Okay, so in this session we are going to solve some problems on PCM. Now PCM topic is covered in module 3, and module 3 is covered by CO3, it is course outcome 3. So the course outcome 3 states illustrate the concept of pulse modulation schemes, demodulation, sampling, quantization, and coding for obtaining of digital data. So this outcome all are going to explain how to convert an analog signal into digital one, and what are the steps involved to convert an analog signal into digital one. So in previously we discussed what is modulation, what is demodulation, what is sampling, and what is quantization. All are discussed in theory, and again problems also covered on sampling and quantization also. Okay, now we are going to solve the problems on pulse code modulation. So this is the first problem. A PCM system uses a uniform quantizer followed by a 7-bit encoder. The bitrate of the system is 50 Mbps. Now they ask, what is the message bandwidth for which the system operates, and determine the output signal to quantizing noise ratio when a sinusoidal modulating wave of frequency 1 MHz is applied to the input. So to solve this problem, first we must know the PCM system. So in PCM system or any digital system, what we require? First we require an source. From that source is applied to the sampler, and then we're having quantizer. Then after we're having encoder. So already we know that an analog signal is converted into discrete one, and the discrete signal which is going to apply to the encoder, then we get the digital signal. Okay, so first we are going to convert continuous signal into a discrete. So discrete means here the pure form of discrete signal. That means it is both in time and amplitude, it is going to discrete. So whereas the sampler which is going to discrete in time domain, whereas the quantizer discrete in amplitude domain. So now the output of the quantizer is a pure form of discrete signal. That discrete signal is applied to encoder. So that's why here a PCM system uses a uniform quantizer followed by a 7-bit encoder. That means after quantizer we're having encoder. Okay. Now again quantizer we're having two varieties, uniform quantizer and non-uniform quantizer. But in this problem they use the uniform quantizer, and they given the bitrate is 50 megabits per second, and the encoder is 7-bit. Okay, so by using this data we are going to solve how to find the message bandwidth, and we are going to determine the SNR output. Okay, let us start the solve the problem. So first given data, so they given the bitrate as RB, which is equal to 50 into 10 power 6 Mbps, and encoder is a 7-bit encoder, so N is 7. Okay, So in the first problem, we are going to find the message bandwidth. That is, we're going to find the W. Okay. So TS is equal to 1 by 2W. You know that. TS is the sampling duration. But they're not given here Fs. But how are we going to find? That is going to find from N TB. That is equal to 1 by 2W. Okay. So here I require W only. So W is equal to 1 by 2N TB. But they're not given a TB. So here you can it has 1 by 2N into 1 by RB. Now we know that N value, we know that RB value. Okay. So again you go to substitute. So 2 into 7 into 1 by 50 into 10 power 6. 50 into 10 power 6. So by using calci, we can find this answer is 3.57 megahertz. So this is the first problem. Or they ask message bandwidth. So the W is the message bandwidth. It is 3.57 megahertz we got. And they ask the second one. The second problem, second bit in this problem, they ask SNR, signal to noise ratio. Okay. So we know the signal to noise ratio formula. It is P by sigma square Q. P by sigma square Q. What is P? P is the average power for the message signal C of T, you can consider, or M of T, whatever it may be. And sigma square Q is the mean square of the quantization, mean square error of the quantization error. Why? Because here we're using the quantizer. So in this process, we're having some error. So that error is called as quantization error. So already you know that quantization error is nothing but the difference between the input signal to the quantizer signal. Okay. So this is a formula, SNR, signal to noise ratio output is equal to average power divided by mean square of the quantization error. Okay. So we know that sigma square Q is equal to delta square by 10. Delta square by 12. So this 12 is the mean square error. Delta square Q. Sigma square Q is equal to delta square by 12. So what is delta? Delta is the step size. So already you know delta is equal to 2m max by L. 2m max by L. So here the maximum amplitude of the message signal. M max means the maximum amplitude of the message signal. So we can write this one as 2 AM by L. This is delta step size. So here we go to substitute the delta square is 4 AM square by 12 L. So here I'm going to substitute the delta value. So my delta value is 2 AM by L. But here delta square, there is 4 A square M divided by 12 L. Okay. So this is my sigma square Q. But here I required SNR, not this quantization noise. Okay. So SNR, signal to quantization noise ratio, is equal to P by sigma square Q. So here P is the average power of the message signal. So here AM we can consider as the maximum amplitude of the message signal. So here we can use as A square M by 2. This is my average power, and my quantization noise error, mean square error of the quantization noise is 4 am square divided by 12L. So after solving this one, what you got? Here this am square is going to cancel, and finally we got 1.5L. This is my SNR. 1.5L. What is L here? L is the representation levels or quantization levels. So here you can substitute L value, L equal to 2 power n. Again you can continue this one, L equal to 2 power n. So 1.5 into 2 power n. 1.5 into 2 power n. So 2 power n. N defines the number of bits. Okay. So here we can use this SNR as in dBs. So we can apply 10 log base 10 for this 1.5L. Okay. So now the SNR is in dBs. Okay. So here I go to write this one. So here you can write this one. SNR output is equal to 1.5L, that is equal to 1.22 power n. So here I am going to convert this SNR into dBs. Then you can apply 10 log base 10 of this 1.5 into 2 power n. Okay. So again you go to apply this 10 log base 10 into 1.5 plus 10 log into 2 power n. So all we get solving this one, simply get it is 1.7 plus 6n. 1.7 plus 6n. So this is directly in dBs. This value is in dBs. Why we are using 10 log base 10? So here we know that n value. Then you can directly get this dB. Okay. So what is n value? N is 7, already given the problem. So SNR output in dBs is equal to 1.7 plus 6 into 7. 6 7 is 42 plus this one you got 43.7. Okay, 43.7 dB. So this is the solution for this given problem. Okay. So now the second one. Consider an audio signal comprised of the sinusoidal term S of t is equal to 3 cos of 500 pi t. So in this problem, the first one, find the signal to quantization noise ratio when this is quantized using 10-bit PCM. And second one, how many bits of quantization are needed to achieve a signal to quantization noise ratio of at least 40 dB. Okay. So here the given audio signal, that is 3 cos 500 pi t, and another given data is n bit. So here the number of bits is 10 bit. Okay. So this is for the first bit in this problem. Okay. They given 2 bits to solve this problem. Okay. Okay. Now our given signal is x of t or m of t, whatever it may be, is 3 cos 500 t. 3 cos 500 t. Okay. So this one. And AM, amplitude signal, is here it shows 3 volts as 3 simply. Why amplitude in volts? So that's why it is 3 volts. And what is the SNR output? So generally this SNR value is directly as 1.76 plus 6n, but approximately you can use 1.8 also. Okay, here 1.76 plus 6n. This is for PCM. PCM SNR output is 1.76 plus 6n accurately, but approximately we can use 1.8 plus 6n also. Okay, anyone you can use this one. So here I am using 1.8 plus 6n for second one. I'm using. So SNR output is equal to 1.8 plus 6n. Here n is also given for the first bit is 10. Okay. So here you can substitute 1.8 plus 6 into 10. So 60 plus 1.8 is 61.8 dB. This one. This is the first problem. Okay. Now coming to the second problem. So the second problem, they ask the SNR value is at least 40 dB. At least 40 dB. So SNR output is equal to 1.8 plus 6n is at least 40 dB. Now what are the number of bits required to satisfy this one? Okay. So here you can send this 1.8 to other side 40 dB. So 40 minus 1.8. So 6n is equal to this 40 minus 1.8 divided by 6. Okay. So 6n greater than equal to 40 minus 1.8. So n is equal to 40 minus 1.8 divided by 6. Okay. So approximately we get n is greater than equal to 6.36. So but the n must be a full form, not here 6.36. So round off to this integer value as n equal to 7. So n approximately equal to 7 bits are required for at least 40 dB SNR get. So this is the second problem for that given. Okay. Now third one. In a binary PCM system, the output signal to quantization noise ratio is to be held to a minimum value of 40 dB. Determine the number of required levels and find the corresponding output signal to quantizing noise ratio. Okay. So this is my given problem. For this problem, we are going to find L, number of required levels, and find the SNR output also. Okay. Yeah. So we know that L is reference levels is 2 power n, L equal to 2 power n. Okay. And what the SNR output is equal to 1.76 plus 6n. This one. This is my signal to quantization noise ratio. Okay. So this in this problem they given 40 dB. The minimum SN output is 40 dB. Okay, in dBs. So the given SNR dB is 40 dB. Now, so convert this 40 dB into value. So the SNR output is equal to 10,000. So convert this one into 40 dB as 10,000 value. So here you are going to find this L value. Yes. So L equal to square root of 2 by 3 SNR output. SNR output. So what is my SNR in value? That is 2 by 3 of 10,000. So here we are going to substitute this 10,000. So again solve this one. So it is nearly 82. But exact value is 81.6, but approximates 82. Okay. So L equal to 2 power n and n equal to log 2 n. Okay. So here we go to substitute L value 82. So log 2 82. Then we got 6.36. So again it is going to approximate 7 from the given value we are finding. So why because here the SNR is given as 10,000 40 dB, minimum 40 dB. So we converting 40 dB into a value that is 10,000. From that 10,000 go to find the L value. From that L value go to find the N value, number of bits. Okay. So by using this, L equal to 2 power N. For second bit we are starting. So 2 power N means 2 power 7. So what you got? So you can use directly in terms of 2 to 7 times or directly 2 power 7. You got 128. So L equal to 128 levels. Okay. The second bit corresponding SNR. Okay. So SNR output for the corresponding N value. Okay. So 1.76 plus 6N. So what is my N? 7 here. So 1.76 plus 6 into 7. So 6 M's are 43 plus 1. We got 43.76 dB. Okay. So this we got for this so given problem. We got the solution. Okay. Now coming to the fourth one. Bandwidth of the input to pulse code modulator is restricted to 4 kHz. The input varies from minus 3 volts to plus 3 volts and has the average power of 30 milliwatt. The required signal to quantization noise power ratio is 20 dB. The modulator produces binary output. Assume uniform quantization. Calculate the number of bits required per sample. Okay. So here we are going to solve. So my SNR dB is equal to 20 dB. SNR is given as 20 dB. So from this you can find SNR is equal to in value. It is given dB. So convert this dBs. So how we get the dB? 10 log this 10. We get x that is in dBs. So again you go to find this x value. Then you get it is 100. Okay. Now delta. What is delta? Step size. It is 2m max by L. So simply you can take it as 2a by L. And we know that L value is 2 power n. Okay. And quantization noise. So here the quantization noise we can mention as NQ or sigma q, what it may be. So that is delta square by 12. Already done in the first problem. Similar. Okay. Delta square by 12. So what is delta square here? Delta value is 2a by L. So delta square 4 a square by 12 L square. 12 L square. So here 3 times go to cancel. Then my quantization noise is equal to a square by 3 L square. This one. But what is signal to quantization noise ratio? This is average signal power divided by average quantizing power or noise power. Quantizing noise power. Simply that is equal to average signal power. So P here mentioned that is 30 milliwatt average power. 30 milliwatt in the problem they given 30 milliwatt divided by this average quantizing power is a square by 3 L square. This one. And here my signal to coordination ratio in value is this 100. So you go to substitute here 100. Okay. So here what our aim? Our aim is to find this L. Okay. So in the next slide, here we go to write L is equal to square root of 30 into 10 power minus 3 power, signal power divided by 3 into 100, 3.8 square. So finally we got 126.67. We got 126.67. So this is my L. So here the nearest reference level is 128. So approximately it is 128. Okay. So L value is 128. From this, what is N? So N equal to 7. This one. Okay. Coming to the fifth one, the bandwidth of TV video plus audio signal is 4.5 MHz. If this signal is converted into PCM bit stream with 1024 quantization levels, determine number of bits per second of the resulting signal. Assume that the signal is sampled at the rate 20% above Nyquist rate. Okay, above the Nyquist rate. So here the given FM, it is this one. So FM is equal to 4.5 megahertz and L is given. Here the L is 1024. Reference levels are quantization levels or 1024. So this is the given data. Okay. And another clue is FS is 20% above the Nyquist rate. 20% above the Nyquist rate. So these are the given data. So 20% above means here that is 1.2 into 2 FM. Okay. So already they given FM 4.5 megahertz. Okay. So by using this given data, we are going to find the number of bits are required. Very simple problem. So first you go to find the FS, that is 1.2 into 2 FM, that is 4.5 megahertz. 2 into 4.5 megahertz. So finally we got 10.8 megahertz. This is my FS. Okay. And L value is 1024. Already we know that L value is 2 power n. Then my n equal to log 2 1024. This is the way, actual way. Then you are using terms of multiplication of 2. Okay. So now n is 10. N is 10. By using calculus you can directly. And the bits per second bit rate RB is equal to NFS. NFS. So what is N? 10. What is Fs? 10.8 megahertz. But here this megahertz is converted to megabits per second. This is the bit rate. So how many bits are transmitted for a second? Okay. So it is 108 Mbps. Okay. So this is the bit rate. So coming to the sixth one. A compact disc CD records audio signals digitally by PCM. Assume audio signals bandwidth to be 15 kilohertz if signals are sampled at a rate 20% above Nyquist rate for practical reasons and the samples are quantized into 65,536 levels. Determine bits per second required to encode the signal and minimum bandwidth required to transmit encoded signal. Okay, so this is the given problem. So the given signal bandwidth, and again here also Fs is 20% above the Nyquist rate, and the given L value is 65,536. Okay, so this is the given data. By using this data, we are going to find number of bits. Okay, yes. So first you go to write the given data FM is 15 kilohertz and Fs is equal to 1.2 into 2 FM. Already we know that. So it is 2.4 into 15 kilo. Why? Because 20% above. Okay, 20% above the Nyquist rate sampling rate. So here Fs is equal to 36 kilohertz. Fs is equal to 36 kilo. And another clue is L value, different levels. There is 65,536 they given. So again, you go to find n. L equal to 2 power n, or you can write n equal to log 2 L. So you can substitute this here. So this is easy by using calci. Okay, so log to 65,536. So by using calci, we get n value is 16. N value is 16. And next one is the signaling rate. So signaling rate is NFS simply, or equal to NFS. So my N value is 60 and my Fs is 36 kilo. Okay. Then again you get 576 kbps. Okay. This one. And another bit is there in this problem. What that one? Minimum bandwidth. So minimum bandwidth is equal to 1 by 2 of signaling rate. Generally we take this one. Minimum bandwidth is equal to 1 by 2 of signaling rate. So 1 by 2 of what is the signaling rate? Already got 576 kbps. Okay. So here 2 times and 88 kilohertz. So this is the minimum bandwidth. The minimum bandwidth is 288 kilohertz. Okay. Coming to the seventh one. The output signal to noise ratio of a 10-bit PCM was found to be 30 dB. The desired SNR is 42 dB. It was decided to increase the SNR to the desired value by increasing the number of quantization levels. Find the fractional increase in transmission bandwidth required for this increase in SNR. Okay. So initially the SNR is 30 dB and increase it to 42. Okay. So in this increment, what are the increase in transmission bandwidth? They ask find the fractional increase in transmission bandwidth. Okay. So coming to the problem. So here go to solute. So first to obtain number of bits for 42 dB. Okay. So SNR output in dBs is equal to 1.8 plus 6n. All this in dBs. Okay. This one is in dBs. So the above equation shows that SNR increases by 6 dB with every bit. Understand? Here this one indicates for every bit increase 6 dB. Okay. So SNR is equal to 30 dB for 10 bits. SNR equal to 30 dB for 10 bits. But the desired SNR is 42 dB. So here the SNR is rise. So here the rise in SNR is 42 minus 30 is 12 dB. So for 1 bit rise it requires 6 dB. So 2 dB increase means 2 bits are required. Here the increment of dB is 12 dB. Sorry, 12 dB is increasing. So for 6 dB, for 1 bit increment 6 dB required. So 12 dB increment. So how many bits? 2 bits are increased. Okay. So n value is 10 plus 2. So 12 bits are required. Okay. Now what is the fractional bandwidth? Fractional increase in bandwidth. So the bandwidth is equal to 1 by 2 of NFS. So NF is nothing but bit rate, half of the bit rate. The bandwidth is equal to 1 by 2 of bit rate. Okay. So first you go to find the bandwidth for 10 bits, then after 12 bits. Okay. So here the bandwidth for 10 bits is equal to 1 by 2 of, here n is 10, Fs already taken as usual 10 Fs, then it is 5 Fs. Why? Because here they required fractional increase. Okay. So Bt is 12 bits, then 1 by 2 of 12 Fs. So it is 6 Fs. Now what is the fractional increase in bandwidth? So we are going to take from 6 Fs to 5 Fs. Okay. So coming to here, fractional increase in Bt is equal to 6 Fs minus 5 Fs divided by 5 Fs into 100. Okay. So solving this one, we get 20%. So this is a 20% increase in bandwidth. Okay. We are coming to the 8th one. The T1 carrier system used in digital telephony multiplexes 24 voice channels based on 8-bit PCM. Each voice signal is usually passed through a low-pass filter with cutoff frequency 3.4 kHz. The filtered signal is sampled at 8 kHz. In addition, a single bit is added at the end of a frame for the purpose of synchronization. Calculate the duration of each bit, and second bit is the resultant transmission rate, and third one is the maximum required transmission bandwidth. Okay. So this is the problem. Actually this is a multiplexing system. Okay. This problem is regarding with the multiplexes and with the PCM. Okay. So this question may come in 2 ways. Now here you go to find the first one is duration of each bit. Duration of each bit. Duration of each bit. So here the signals are sampled at 8 kilohertz. So the time between any two successive samples of the same channel will be 1 by 8000. 1 by 8000. So here we got 125 microsecond. Okay, 125 microsecond. Why? Because this is T1. So frames, we require the frames. So one frame, in one frame of 125. So that means here the frame is 125 microsecond. Now bits for frame. So bits per frame, bits per frame is equal to 24 channels by frame into 8 bits per channel plus 1 bit for synchronization. Already given in this problem. Here they are given 24 voice channels, okay, and sample at 8 kilohertz, and it is 8 bit PCM, and 1 bit is given for the synchronization. So 24 channels for frame into 8 bits for channel plus 1 bit. Okay. So now we get to 193 bits. So each frame contains 193 bits. So this is 193 bits. So time duration of one bit that equal to time duration of one frame divided by bits per frame. So here we got 125 microsecond. So 125 microsecond divided by 193. Why? Because here bits per frame is 193 got. So bits per frame is 193 and time duration for one frame is 125 microsecond. So now we got time duration of one bit is 0.6476 microseconds per bit. This one. Okay. Now the second one is transmission rate. Why? Because in this problem they asked 3 bits in this problem. One is bit duration, another is a transmission rate. So RB is equal to 1 by duration of 1 bit sampling. So that is 1 by, previously find a 0.476 into 10 power minus 6. So it is in megabits per second simply. So that is 1.54 Mbps. This is the transmission rate. And third one is the transmission bandwidth. So the transmission bandwidth, that is equal to BT is approximately 1 by 2 of RB. Already we seen in previous problems also. Okay. So that is equal to 1 by 2 of 1.544 mega. Okay. So solving this, we got 772 kilohertz. So this is the bandwidth. This is the bandwidth for this given problem. Okay. Now another problem, ninth one. So the ninth one is 24 voice channels of 4 kHz bandwidth, each sampled at Nyquist rate and encoded into 8-bit PCM or time division multiplex with 1-bit frame as a synchronization bit. What is the bit rate at the output of multiplexers? So this problem also regarding with multiplexers. So here also it is in frames and 1 bit as synchronization bit. Okay. So first given data n Kaplan indicates the number of channels, that is 24. Okay, and what they given W, the bandwidth is 4 kilohertz, and small n, number of bits for encoded n. Okay, so this is the given data. By this given data, we are going to find the bit rate at the output of the multiplexers. Okay. Yes. So first Nyquist rate. So Nyquist is 2W. So what is W? Given 4 kilohertz. So 8 kilohertz. Okay. So now 24 voice channels are transmitted in one frame. So each of the channel contains 8 bits. So 1 bit is added as synchronization bit. Okay. So you go to find bits in one frame. It is similar to the previous problem also. Okay. So 24 into 8 plus 1. 24 channels and each having 8 bits plus 1 bit is for synchronization. So it is also got 193 bits for frame. 193 bits for frame. Okay. Now frames are transmitted at the Nyquist rate. Hence, bit rate at the outputs of multiplexers will be. So bit rate is equal to number of bits per frame into Nyquist rate. Number of bits per frame into Nyquist rate. That is 193 into what is the Nyquist rate? 8000 hertz. Okay. So then we got 1.544 into 10 power 6 bits per second. So actually it is similar to previous one. So in previous problem also get the bit rate as 1.54 megabits per second. Okay. Yeah. Coming to the last one. The information in an analog waveform with the maximum frequency FM is equal to 3 kilohertz is to be transmitted over an M level PCM system where the number of pulse levels is M is equal to 16. So here analog waveform is transmitted into a digital one. Okay. So the analog waveform here having the frequency is 3 kilohertz is to be transmitted over a M level PCM system. So generally we are having a binary PCM system, but here it is M level, that is M array we are using, where the M value is given as 16. Now what is the maximum number of bits per sample that should be used in this PCM system? And second bit is what is the minimum sampling rate and what is the resulting bit transmission rate. Okay. Okay. Coming to this first one, number of levels is 16. Okay. So here number of levels is just equal to m, that is 16. So L equal to 2 power n, that is 16. So n value is nothing but 4. Number of bits is 4. And second one, Fm or W is equal to 3 kilohertz. Okay. So Fs greater than equal to 2W. That is the next, right? So it is greater than equal to 2 into 3 kilo. So Fs is greater than equal to 6 kilo. Okay. So this is a sampling frequency. Now R is equal to N into Fs. So what is N? Here 4, Fs 6. So that is equal to 24 kilohertz. But this is kpbs. This is RB bit rate or transmission rate. That is 64 kilobits per second. You can transmit to a PCM system. Okay. So this is some problems on PCM system. I hope you are understand. And the references here, the current information taken from Communication Systems by Simon Hacking Foundation and Digital Commission by Dr. J.S. Chitode. Okay, and same as Chakrabarti textbook is also considered to solve these problems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.